Welcome to the class of computer network. In this session, we are going to discuss the data link layer. Data link layer works between two hosts which are directly connected in some sense. Direct connection could be point to point or it could be broadcast. Data link layer is responsible for converting data stream to signal. So the major responsibility is number one is converting data stream to signals bit by bit, and to send that over the dedicated hardware. Okay, and the second responsibility is, you can say, the framing. We will talk about the framing in the session. Then it provides flow control, error control, and synchronization. So you can understand that the station may have different speed or capacity. Now it is the responsibility of data link layer to ensure both machine to exchange data on the same speed. So this is what the flow control is. So let us discuss the flow control. So let's say there are sender and receiver. Two machines, one is sending sender, one is called sender, another one which is receiving is called as receiver. Let's say it has a sequence of frames. There are, let's say, I'm just drawing the layers: physical layer, data link layer, network layer. Similarly, this machine will also have physical layer, data link layer, and network layer. Why I'm discussing this only three layer over here? Because the data link layer basically does the hope to hope communication, and in the hope to hope communication there is no need of discussing the further layer, which are transport layer and upward layer, because the transport layer will come into picture when there is a concept of uh, you know service to service delivery, and network layer is something what is going to deliver your end to end delivery. Okay, so this is the sender and receiver could be just a part of the whole communication, as we have discussed in the previous classes. Sender sends the frame at a very high speed. Let's assume that. So if at another end, so if at the other end buffer is full, so it can't store the frames. Now the next frame will be discarded. So there is a need of synchronization and flow control between sender and receiver. So the sender's speed could be, could be a higher speed, and the receiver speed is receiving speed is something which is slow. So what would happen actually when this the sequence of frame will be transferred? There would be, a lot of buffer would be created, and once the size of buffer is being full, in that case that the frames which are sent by sender are going to be discarded at the receiver end, and then we'll have a data loss over there at the receiver end. So that's why there is a need of synchronization between the speed of sender and receiver. Also there should be a need of the flow control, that to which speed the sender should send the data, so that receiver will receive all the data and there should not be no data loss. So now we will discuss the flow control mechanism provided by the data link layer. So it can be majorly divided in two categories. One is stop and wait protocol, Another one is sliding window protocol. The sliding window protocol can be further divided in two sections. One is go back and ARQ and selective reject or repeat ARQ. Now, the in the sliding window protocol, what actually happened in this flow control mechanism, both sender and receiver agree on the number of data frames after which the acknowledgement should be sent. Okay. Before discussing the flow control mechanism, let me show you the further categorization of the data link layer, and I can say data link layer can be categorized, or you can say further divided in two parts. One is logical link layer, or you can say logical link control, and another one is media access control. Here, this logical link control deals with the protocols like flow control and error control, while uh, the media access control actually deals with actual control of media. So if in some question, if it specifically it is being asked that which part of data link layer actually does or you can say the provide the flow control and error control, you can answer logical link control, or you can say logical link layer. Now we'll start with our section, which is stop and wait protocol, or you can say the stop and wait ARQ, where ARQ is nothing but automatic repeated request. So we'll start with stop and wait. In the stop and wait protocol, sender sends only one frame at a time and wait for the acknowledgement frame from the receiver. So it sends only one frame at a time and wait for acknowledgement from the receiver. So it is something like that. Let's say we have sender over here and we have receiver over here, and we have, let's say, 0101 the data. Okay, and this is something which is frame 0, this is frame 1, this is frame 2, and so on. Now, as I said that in the stop and wait protocol, sender sends only one frame at a time. That is, only at a time, only either 0 will send, or 1 will send, or a 0 will send, or next whatever the upcoming frames are. So senders will send the, let's say, the first frame, which is 0, and it will wait for the acknowledgement from the receiver side before sending the next frame. So until unless it will receive the acknowledgement from the receiver, it will wait for the next frame to send. So what will happen? The receiver will send the acknowledgement that it has received the frame 0, and will send the acknowledgement 1. Here you can say that once acknowledgement 1 is being received by the sender, okay, then it will send the frame number 1. okay. And once it will once is being received by the receiver, it will ask for the next frame and will send the ACK 0. As you can say, you may see over here that there is only either 0 and 1. So that's why the ACK would be ACK 0 or ACK 1. So here ACK 1 actually defines that receiver is now expecting the next frame, which is 1, to be sent, and it shows that the 0 is being received. Now we have to calculate over here something which are from numerical point of view, which are important, and which is number one is frame transmission time. We call it TT, time of transmission. It is the time taken by the system to transmit a frame into a network. And it can be calculated as TT would be frame size upon data rate, where frame size, let's say, can be some f bits. The size would be in terms of bits, okay, kilobyte or something, okay. And the data rate would be some bits per second. Next terminology is your propagation delay, which we call TP, time for proposition, okay. And this is something, what is the time taken by single bit to propagate from one end to another end. And this is something you can assert that this is the sender and this is the receiver. Now the bit is being transferred from sender to receiver, and how much time it takes from reaching from sender to receiver, this would be your propagation delay. And to calculate the propagation delay, you must have known the distance between sender and receiver. So let us assume that d is the distance between the sender and receiver, and v is the speed of signal. So because the transmission is happening in terms of signal, so the time taken would be from one single bit to from receiver to from sender to receiver would be distance upon the velocity, where distance d is nothing but the distance between sender and receiver, and v is the speed of signal. Now there is one more terminology which we call a round trip time, or you can say sometimes we call it round trip propagation delay, which is nothing but twice of TP. Okay, so what actually we mean by the round trip time, okay, and that is something that you can say from sending from sending a bit from the sender to receiver and going back the bit from receiver to sender. So it is something sending a bit from sender to receiver and receiving from receiver to sender the acknowledgement, because receiver is going to send the acknowledgement to the sender, and then only sender is going to send the next bit. So the round trip time is nothing but the time taken by a single bit to travel from sender to receiver plus the time taken by the acknowledgement to receive to travel from receiver to sender. In both the cases, you can see the distance is not going to vary and the signal speed is not going to vary, and that's why the this is what we call the uh, total round trip time will coming out to be twice of TP. So now let us see, how this going to happen in actual scenario. So let's say this is the sender and this is the receiver. Initially, let's say it has a sequence of 0 1 0 1 bits, and let's say the 0 is being sent. So what actually happened from the system? Okay, from the system of sender, the receive the bit, or you can say the frame one, the time taken by the frame one from the system to come into the network is what we call the TT. So we can say that this 0 is coming in the network, or you can say in the starting of network, is the time taken is TT, which is your transmission time. Let's say at t is equal to 0 we have started, and tt time it has taken for the frame to come into network. At this time, let's say this is the time frame. So at t is equal to 0 we have started, and at time t is equal to tt, what actually happened at this time, the frame is completely transferred into network. Then this frame is going to travel from sender to receiver, and the time would be TP, which is the propagation delay. So this frame is going to travel from sender to receiver, and the time will taken by the frame would be TP. So if we look at the time frame, we have started at time t is equal to 0. At time t is equal to tt, the complete frame is being is being transferred into network, and at time t is equal to tt plus tp, we will the receiver will receive the uh, you can say the you know uh, the receiver will receive the frame. Okay, by that time, t is equal to tt plus tp, the frame is completely received at the receiver end. Then what will happen? Then after this time, what will the receiver do? Receiver will process the frame, and after that receiver will generate a acknowledgement. Okay, so for an acknowledgement to come into network from the system of receiver, the time taken would be TT for acknowledgement, let's say. Okay, now this acknowledgement will be transferred from receiver to sender, and the time taken by this acknowledgement to travel and reaching to the sender will be again TP, because TP is going to be same for both acknowledgement and both the frame, because it does not depend on the size of frame or something. It only depend on the distance between sender and receiver and the velocity of signal. And for both acknowledgement and both frame, the distance is not going to change and the velocity is not going to change. So the time taken by ACK, or you can say acknowledgement, reaching, transferred from receiver and reaching to sender is going to be TP. So by this time, you can say by this time t is equal to tt plus 2tp. Okay, because tt plus, at time tt plus tp, the receiver has received the frame, then receiver process the frame and generate the acknowledgement, and the time taken by the acknowledgement would be, you can say that again, plus tt of ack. So there are, you can see that I have not actually considered some of the time over here. So I can show you over here. You can say initially the time TT was taken for a frame to come into network at the sender end. Then the time TP was taken by the frame to reach to the receiver. Then there is a processing time of the frame at the receiver end. After, once the frame is processed, receiver is going to generate the acknowledgement. So the time, and then time taken by acknowledgement to come into network would be tt of ack. Then TP time will be taken by frame, or sorry, by the acknowledgement to reach to the sender, and then sender is going to process the acknowledgement. So processing time of ACK at sender end. So this is what the a complete cycle of, you can say, the one frame is being transferred from sender to receiver and receiving the acknowledgement properly. So this is what we call the cycle time. Now the processing time of a frame is very negligible in compared to TT and TP, because we have very fast processors and it doesn't take much time, so that's why we can ignore it. Similarly, that processing time of the sender, processing time of the acknowledgement is also going to be very less, so we can simply ignore it. And we can also ignore the time, transmission time of ACK, because the size of ACK is too less. Okay, so just because, and that the TT is nothing but the time, transmission time is nothing but the frame size upon data rate. And as, because if the frame size is too less, then the TT is going to be very less. So we can, for the acknowledgement, the frame size is going to be very less, and hence we can ignore this time also. And you can approximately calculate the cycle time as TT plus TP and TP, which is twice of TP. Okay, then here we can see that it can also be taken as, if we can take TT in common, and we can have 2 twice of TP upon TT. We can we may give a term, let's say A, for where A is TP upon TT. Okay, so this is what the cycle time is. Here you can see that the sender is active for how much time. If you look back, the sender was active only for the time when the sender was sending the frame. Okay, the frame one, or you can say the another frame. So sender was active in a cycle time. Sender was active only for a part where the frame was coming into network. Okay, so we can say, and the time for a frame to come into network was tt. So we can say that the active time of sender was nothing but the transmission time only. Now, by this formulas, we can also calculate the channel utilization, which is nothing but the active time of sender divided by cycle time. So the thing is, out of a cycle time, okay, how much time when the sender was active, that is what we called as channel utilization. So you can say this channel utilization formula can be active time of sender is nothing but tt, and cycle time is nothing but tt plus 2tp. Okay, so here this can also be calculated as tt on tt plus 1 plus 2a, or it can be 1 upon 1 plus 2a. So this is what the channel utilization is. Similarly, there is one more terminology that we call the throughput, and throughput is the data transmitted into network upon cycle time. So the data which was sent into the network is nothing but equal to the frame size, and once we divide it by the cycle time, so you can say in a cycle how much data is being transmitted into network, that is what our throughput is. So that can be calculated. The frame size is nothing but, let's say, whatever the size is, frame size, and cycle time is tt plus 2tp. So this is what the formula of throughput. Okay, so now you can say that throughput can also be calculated in terms of, if we look back at the formula of channel utilization, where the channel utilization was nothing but the tt upon tt plus 2tp. From here we can say that tt plus 2tp is nothing but channel utilization, or you can say the efficiency into tt. So if I replace this tt plus 2tp by channel utilization into tt. So this can be, further one more formula, and uh, if I replace this the formula of tt, you can see, you all knows that tt is nothing but the frame size upon data rate. Okay, so here frame size can be tt into data rate. So frame size can be tt into data rate. Oh, I'm sorry, I did something wrong. You can see in the previous case this tt is coming out to be tt plus 2tp is coming out to be tt upon channel utilization. And once we have done this, then this would be frame size upon tt plus 2tp. I can replace it by tt divide by channel utilization, and I can replace this frame size by uh, data rate into tt. So I can say tt into data rate into channel efficiency or channel utilization. So we may have found another formula for throughput is data rate into channel utilization, or you can say the efficiency of channel. Sometimes we can call it channel efficiency. That is what the throughput is. So we got two different formula for the throughput. Now we'll solve certain question about the related to this channel utilization and throughput.